Imagine for a second that you could, like, reach up into the sky, grab the sun right at high noon, and just pin it there.
Oh, wow.
That's
Okay.
like you just refuse to let it set. You leave it blazing hour after hour, day after day. What do you think would happen to the world underneath all that unending light?
I mean, it's a deeply unnatural image, right? You'd expect absolute chaos.
Total meltdown.
Exactly, a complete breakdown of the natural order because biological systems they rely on the relief of darkness just as much as they rely on the energy of the sun. It's supposed to be binary, day and night, action and well, rest.
Right, you'd think the whole system would just shatter under that kind of pressure. But what if you force that unending sun onto a closed ecosystem? Say, a tropical fish tank.
Oh man, that is quite the visual.
It is. And we actually got our hands on some truly fascinating source material for you today. It's an update from a journal titled Notes on Fishkeeping.
Which is such a great resource, by the way.
It really is. Specifically, we're looking at part 267, published by an aquarist named Ang. And in this deep dive, we are exploring exactly what happens when you take the biological rule book of a well-established environment and just, throw it completely out the window.
And that number, part 267, that's actually a crucial piece of context for you, the listener.
Yeah, definitely.
Because, I mean, this isn't someone who just bought their first glass box yesterday at the pet store. For over 260 entries, this aquarist has been meticulously documenting their tanks.
They know what they're doing.
Exactly. They've established these incredibly solid baselines. They know the rhythms of these ecosystems inside and out. So when they decide to tweak a fundamental environmental variable, it's not just random, it's a very deliberate disruption.
Okay, let's unpack this. The disruption Ang chose was shifting from what they call a standard 12-hour tropical photo period to just leaving the aquarium LEDs on 24 hours a day.
7 days a week.
Yep, for the past few weeks now. But before we even get to the results, we really need to understand the baseline here. What exactly is a 12-hour tropical photo period doing for the things living in that water?
Well, what's fascinating here is how carefully a 12-hour cycle is designed to mimic nature.
Right, because of the equator.
Exactly. Near the equator, day and night are roughly split, 12 hours each. And the aquatic life, the fish, the live plants, the microscopic organisms.
All the invisible stuff?
Yeah, all of it. They haven't just adapted to that rhythm, they are literally biologically programmed by it. During those 12 hours of light, plants are photosynthesizing.
So they're like eating light.
Basically, yeah. They are eagerly consuming carbon dioxide and producing oxygen.
And then the sun goes down. Or, well, in this case, the literal timer clicks off.
Right, and a massive biological switch flips. Without light, photosynthesis just stops. The plants actually reverse their process.
Wait, they reverse it?
Yeah, they begin consuming oxygen and releasing carbon dioxide just like the fish do.
Oh, wow. I didn't realize they competed for oxygen at night.
They absolutely do. And meanwhile, the fish use that dark period to rest, to, repair cellular damage, to lower their stress hormones. The darkness is essentially a mandatory biological reset button.
So by pinning the sun to the sky, by leaving those LEDs on 24/7, Ang is essentially taping down the accelerator pedal.
That's a great way to put it.
The plants are stuck in hyperdrive. The fish have no darkness to signal rest. The whole system is just awake forever. I mean, that sounds exhausting.
It is a massive stress test. You are actively denying the ecosystem its recovery phase.
And naturally, when you run a stress test of that magnitude, you have to look at the immediate physical impacts before you can even begin to understand the biological ones, right? Cause and effect.
You have to. You can't change the energy input without changing the physical reality of the water. Light is energy, and in a closed system, well, that energy has to go somewhere.
I think about it like this. Imagine you leave your oven door slightly open in a really small kitchen during the middle of the summer.
Oh, miserable.
Right. Even if the oven isn't set that high, it's going to fundamentally alter the microclimate of that room over a few hours. Now, we tend to think of LED lights as relatively cool, right?
Sure, compared to the old ones.
Yeah, especially compared to those scorching old-school incandescent or fluorescent bulbs that used to literally melt plastic aquarium hoods. But what happens when even a quote-unquote cool LED literally never turns off?
Well, your oven analogy is on the right track regarding the accumulation of heat. But, in a fish tank, you're not just dealing with warm air. You're dealing with the thermal dynamics of water.
Which holds heat really well.
Exactly. It's a continuous thermal input. And Ang notes this exact phenomenon in the journal. They observed that the tank water is evaporating at a significantly faster rate than it did on the normal 12-hour cycle.
Which totally makes sense. More heat, more evaporation.
Right, but Ang makes a very astute observation here. They don't just blame the unending lights for all the water loss.
Oh, what else is doing it?
Well, they attribute the rapid evaporation to a specific combination of two factors. It's the cumulative heat generated by those 24/7 LEDs and what they call the current weather.
Wait, the weather outside the tank?
Mm.
Like the weather in the aquarist's actual living room?
Precisely. And this is such a critical concept for anyone trying to understand controlled environments. We look at a glass aquarium and we see a firm boundary, right?
It looks like a bubble.
We think of it as an isolated, self-contained little world. But it's not isolated at all. Glass is an excellent thermal conductor.
Oh, right. So the heat from the room easily transfers right through the glass into the water.
Yes. You have the internal heat from the LEDs constantly pushing the water temperature up from the top. And then whatever the current summer weather is doing to the room's ambient temperature, well, that's compounding the effect from the sides.
It's attacking from all angles.
Pretty much.
Oh,
The
wow.
two heat sources gang up on the water, driving up the rate of evaporation much, much faster than either would alone.
And evaporation isn't just, water magically disappearing. When water leaves the system as a gas, it leaves behind all the dissolved minerals.
Oh, the fish waste.
The nitrates, yeah. Everything in that tank gets more concentrated. The physical pressure on the environment is just ramping up. So we have this physical reality established, right?
Sure.
The tank is losing water faster. The heat is constant. The light never stops.
It sounds like a recipe for disaster.
It really does. I mean, if
Right.
I leave my lawn in the blazing sun 24/7, it dies. So what happens to the living things inside this glass box? I'm assuming it just turns into an absolute disaster zone.
You'd completely expect a total biological breaking point, wouldn't you?
Absolutely. But here's where it gets really interesting. If you blast a closed aquatic ecosystem with light for 24 hours a day, shouldn't the whole thing just turn into a stagnant pea soup swamp?
If that's the assumption.
Because light drives algae growth. Unending light should mean unending, uncontrolled algae, right?
That is easily the most logical assumption you could make. Algae are incredibly opportunistic organisms. Unlike, the fancy decorative plants in a tank, algae don't need complex root systems.
They're survivors.
Totally. They don't need carefully balanced fertilizers to get started. They basically just need water and light. And Ang is giving them an infinite supply of light.
But the reality of Ang's findings totally threw me. Completely surprised me.
Yeah, it's not what you expect.
Ang actually describes the results of this extreme experiment as mixed. On one hand, yes, an algae bloom has returned. Ang specifically notes that growth is visibly forming on the glass of the aquarium.
Okay, so the algae is definitely taking advantage of the constant light.
Right, it's coating the walls of the tank. But the twist,
Oh, the twist is wild.
the massive twist that totally defies my swamp expectation, is that Ang notes the water itself remains crystal clear.
Which makes no sense at first glance.
None. I just don't get it. How can the glass be covered in thick algae, but the water is perfectly fine? Is the constant light somehow, bleaching the suspended algae in the water?
No, the light isn't bleaching anything. What you're seeing here is honestly a masterclass in nutrient competition. If we connect this to the bigger picture, we can see why this clear water is such a profound observation.
Okay, break that down for me.
Well, Ang actually contrasts this tank with a specific note about that other tank they've seen, which did turn completely green.
Oh, the dreaded green water. Every fish keeper's nightmare.
Exactly. In the hobby, green water is planktonic algae.
Wait, planktonic, like floating.
Yeah, exactly, the free-floating stuff.
Yeah.
It's microscopic, single-celled algae suspended freely in the water column itself. When a tank turns into green water, the biological system has usually lost its balance entirely.
It's just a free-for-all.
Right. The suspended algae outcompetes everything else and just takes over. But what Ang is observing in this 24/7 light experiment is strictly localized algae growth.
It's just on the glass.
Yes, it's clinging to the glass, forming a thick biofilm, while the water column itself remains pristine.
So why one and not the other? Why does the algae stick to the glass and leave the water completely alone? Is it like some kind of turf war?
A turf war is actually a great way to think about it.
Mm.
Think of the algae on the glass like a massive, fast-growing weed in a garden.
Okay.
If that weed establishes itself early, It spreads its giant leaves over the topsoil, hogging all the sunlight and aggressively sucking up all the water and nutrients from the dirt.
It's stealing all the food.
Exactly. And because that big weed is consuming all the available resources, the other tiny seeds buried in the dirt, which represent our planktonic green water algae, they never even get a chance to sprout.
Wow.
Yeah, they literally starve before they can bloom.
Oh. So the glass algae is acting as this massive nutrient sink.
Bingo.
It's absorbing the unending light, and it's eating up all the nitrates and waste in the water so effectively that the green water algae is essentially starved out of existence.
Precisely. It implies a remarkably complex adaptive balance within this specific tank. Even under the extreme stress test of constant light and rising temperatures, the ecosystem hasn't collapsed into a chaotic monoculture of suspended swamp water.
It fought back.
It did. The existing biology, the glass algae, has formed a bizarre new equilibrium. It's surviving the constant light stress test far better than anyone would predict. The system is bending heavily, but it isn't breaking.
That is wild. The system just, invents a weird, unexpected new normal. The water stays clear, but the glass gets coated, and the water level is dropping faster because of the evaporation.
It's a completely different environment now.
You can really picture this tank right now. It's glowing, it's half covered in green film, it's hot. And because of these cascading physical and biological consequences, Aang is forced to step in. The experiment's results are now dictating the next mechanical steps for the tank's infrastructure.
Which is the very essence of practical, hands-on observation. You intentionally change a variable, the light. You observe the system's reaction, the evaporation, and the localized algae.
Right.
And then you must adjust your infrastructure to compensate for the new reality you've created.
It's like, imagine you decide to build a massive, high-powered crypto mining computer rig in your home office.
Okay, tracking.
You plug it all in, and suddenly the room is incredibly uncomfortably hot. You don't just sit there and sweat, right? You have to go and upgrade your home's air conditioning to deal with the new heat load. You have to handle the downstream effects of your initial choice.
That's a perfect analogy. The 24/7 light was the initial choice. The heat, the evaporation, and the biological turf war are the downstream effects. And Aang's immediate action plan reflects this perfectly.
What do they do?
Well, Aang writes that it is now, quote, probably the right time to start adding sponge filters to all the tanks.
Okay, let's talk about sponge filters, because I think a lot of people just picture a literal kitchen sponge jammed onto a plastic tube.
Right, the yellow ones with the green scrubby pad.
Exactly. But why is that the specific piece of infrastructure Aang pivots to here?
It's a great question because a sponge filter is actually a brilliant piece of low-tech engineering. Mechanically, it works using an air pump. The pump pushes air down a tube into the center of a dense cylindrical sponge.
Okay, so air goes in.
Right. And as those air bubbles rise back up through the tube to escape to the surface, they create a natural vacuum. That vacuum constantly pulls aquarium water through the microscopic pores of the sponge.
So it's sucking all the physical debris out of the water, like a vacuum cleaner.
It does trap floating debris, yes, but its real power is biological, not mechanical. All those millions of tiny pores inside the sponge provide massive surface area.
For what?
Well, that surface area becomes prime real estate for highly beneficial microscopic bacteria. As the water is pulled through the sponge, these bacteria literally eat the toxic ammonia produced by fish waste, breaking it down into less harmful compounds.
Wait, so by adding the sponge filters, Aang is essentially deploying an army of beneficial bacteria to compete with the algae.
Exactly. You nailed it. The bacteria in the sponge will consume the same nutrients, the nitrogen compounds, that the algae on the glass relies on to grow.
Oh, that's brilliant.
It's another layer of nutrient competition. Plus, all those air bubbles rising out of the sponge filter create constant surface agitation at the top of the water.
Wait, that helps with the heat issue, right?
Yes, it does. Breaking the surface tension increases gas exchange, which allows oxygen in and carbon dioxide out. And it dramatically increases evaporative cooling.
Ah, so it chills the water.
Exactly, which helps counteract the continuous heat from those 24/7 LEDs. It's a single, elegant solution that addresses both the biological algae bloom and the physical temperature rise.
And what I absolutely love about Aang's reasoning here is how wonderfully pragmatic it is. It's
Yeah.
not some highly theoretical lab-grade decision where they had to, order a $2,000 digital filtration array.
Not at all.
Aang literally writes that it's the right time to add these filters. especially since I've got a few spare air pumps and sponges lying around.
This raises an important question about the reality of amateur experimentation in a hobbyist science.
Yeah, it's very relatable.
The beauty of this kind of work is that it's rarely about sterile, perfect conditions. It's about looking at the resources you already have in your closet, spare air pumps, extra sponges, and deploying them creatively to manage a system under stress. You use what you have to solve the problem you created.
Just grabbing stuff out of the garage to fix the ecosystem. And Ang notes that deploying these filters across all the tanks is something to explore soon.
Which perfectly illustrates the endless, iterative loop of the scientific method in practice. Resolving the outcome of one experiment doesn't end the process, it simply triggers the beginning of the next one.
It never stops.
Right. The 24/7 light caused the heat and the algae. That necessitated the sponge filtration. And now, deploying spare sponge filters across all the tanks becomes the next experiment. How will the other tanks react? The ecosystem constantly evolves, and the aquarist has to evolve right alongside it.
You poke the system pushes back, and you adapt. So what does this all mean for you, the listener? We started with a perfectly balanced aquarium running on a standard natural 12-hour tropical photo period.
A very safe baseline.
Right. Then we threw out the rulebook and blasted it with a constant, unrelenting 24/7 sun.
And instead of the total systemic collapse we expected, we saw a complex physical and biological negotiation.
A negotiation, I like that.
Yeah, the cumulative thermal load from the LEDs and the ambient room weather accelerated evaporation, putting all this physical pressure on the tank.
Meanwhile, the biology went to war. The constant light fueled a massive algae boom. But surprisingly, the algae localized entirely to the glass.
Acting as that nutrient sponge we talked about.
Exactly. Starving out the planktonic algae and avoiding the dreaded green water scenario entirely, keeping the water column crystal clear.
And ultimately, that strange new equilibrium forced the aquarists to adapt their infrastructure, utilizing spare parts to deploy sponge filters, increasing beneficial bacteria to compete for nutrients and cooling the water through surface agitation.
I think there is a profound value in exploring this kind of controlled disruption. Sometimes you really do have to push a system far past its assumed limits just to see exactly how it manages to bend.
Because if you never push it, you don't know.
Exactly. If you never push it, you just operate under the assumption that it will instantly shatter. I fully assumed 24 hours of light equaled a ruined, stagnant swamp. But Ang pushed it and revealed an incredibly resilient, adaptive ecosystem instead.
It's a powerful realization about the nature of adaptive equilibrium. Systems, even fragile artificial ones, they don't always break when you overstress them. Often they just invent a highly irregular, unexpected new normal to survive.
Yeah.
And that actually leaves me with this final thought for you to consider. If a delicate aquatic ecosystem can maintain clear water and find a functioning equilibrium under the extreme, completely unnatural stress of an unending sun, what other unbreakable standard rules or strict boundaries in our own lives or our own work environments might we be blindly following out of mere habit rather than actual necessity?
It's good. It makes you wonder how many things we assume would cause total chaos, when really they might just force a clever adaptation. Keep questioning the rulebook. We'll catch you on the next deep dive.